Hi everyone, my name is Mansooreh and I'm a master's student at Concordia University, working under the supervisions of Professors Naderkhani and Mohammadi. Today I want to present my paper on spiking neural networks for SEMG-based hand gesture recognition for the SMC conference 2023. First of all, to talk about some prior works on the topic of hand gesture recognition, which is widely used in HMI devices, robotics, and exoskeletons. I should mention that many different machine learning and deep learning models are proposed recently for the task of automatic SEMG-based gesture recognitions. These models include some conventional methods such as support vector machines and linear discriminant analysis. And also we have a very wide range of simple or advanced deep neural networks, such as convolutional and recurrent neural networks, transformer-based architectures, and hybrid CNN RNN models. And these models have been proven to work very efficiently to classify the hand gestures in many areas of gesture recognition, but despite their general effectiveness, those models suffer from major drawbacks, such as not fully exploiting the temporal and spatial, and specifically in this paper, the neurophysiological characteristics of CMG signals, or being very computationally complex and expensive and require too much time and memory to be trained. In particular, standalone CNN and RNN structures fail to jointly capture the time series and spatial features of SEMG data. Transformers require huge amounts of training data and powerful computational resources, and hybrid architectures are very difficult to optimize because they have very large number of trainable parameters. However, in this paper, we want to propose a framework for hand gesture recognition based on spiking neural networks, and we use the following high-density SEMG dataset. Our dataset contains two grids of rectangular electrodes, two rectangular grids of electrodes, each containing 64 electrodes. So we have 128 electrodes in total. These grids are placed on the extensor and flexor muscles of the forearm, as shown in the following picture. So we have collected a three-dimensional data, which has two-dimension space and one dimension in time, from 19 subjects and for 5 different repetitions and 66 hand gestures. These signals are then low-pass filtered, normalized, and windowed using a window size of 128 samples. And here is the MULA normalization formula that we have used in our paper, which has been shown to outperform the min-max normalization using in many papers in this context. To talk about the spiking neural network based hand gesture recognition, I want to mention that these neural networks do a spatial temporal gesture recognition in an event-based fashion. It means that they are very likely to imitate human brain's cognitive function by using some biologically inspired models of neurons and synapses. They do have specific activation functions with discrete valued spikes, unlike the traditional DNN architectures that use activation functions with continuous values. So they do something like what human brain does and will be more biologically explainable and computationally efficient. These neural networks have been widely used in some contexts of computer vision, like image classification, object tracking, and gesture recognition. And because we found very limited works in the context of EMG-based gesture recognition, we wanted to perform this on our high-density SEMG dataset to see the actual performance of our network. Here we wrote the formula for the specific type of neuron that we have used, which is the leak integrate and fire neuron. Its membrane potential is dependent on the membrane potential in the previous time step, the input current to the neuron, and the activation status of the neuron in the previous time step. And we have two different hyperparameters here, beta, which is the decay rate, and the theta, which is the membrane's threshold. Here I have shown a very basic structure of my SNN framework. I have two linear layers, and I have window sizes of 128 samples. And here I decided to classify 14 different hand gestures, which had 1 degree of freedom in our data set. Here it shows the window, and here this 128 shows the number of electrodes at each time step. The signal for all the electrodes goes to the SNN framework, and some processings are done. And then we go to the specific loss function that we have defined here. In this paper, we show the specific hyperparameters of the SNN-based framework, in which we put the leak integrate and fire threshold to 1 and the decay rate to 0.9. Here we use a specific softmax function, which outputs some discrete values and is designed for spiking neural networks. And then we define our cross-entropy loss function, which is called the cross-entropy rate loss function. Here to classify the gestures at each time step, we calculate the spikes for all the gestures, and then sum the spikes up for all the time steps, and the gesture that has the maximum number of spikes is given as the correct label. Here in our experiments and results, we show that we had a very large range of accuracy, which is from 40% to near 100%. 6 of our subjects had a very good accuracy of 80% to near 100%, but the other subjects did not go well with this SNN framework. And here we show the results for the Wilcoxon's signed rank test, the statistical results, and the box plots and interquartile range of classification accuracy for all the 5 folds. In this picture, we can show that when we use folds 2, 3, 4, 5, I mean the repetitions 2, 3, 4, 5 for the test hold, we do not see a very significant discrepancy between the performances of the pairs of the models. But if we use the first fold as the test set, the network's performance will be very different from other networks. And in this picture, we also show the raster plots of output spiking neurons for subject 16. As you can see here, subject 16 had the best performance, had a very good performance among all the other subjects. And here, for example, we see that for gesture 11, we had the maximum number of spikes, and this gesture is classified completely correctly. And here, between gestures 10 and 3, gesture 3 had more number of spikes in the window of 128. So it is also again classified as the correct hand gesture. As a conclusion and future voice, we can say that in SNNs, depending on the utilized repetition for the test set and also the subject that we are working on, the accuracy differs in a very large range. And if we put the first fold as the test set, the accuracy declines very, very significantly. And also, we can improve the performance and generalizability of the SNN frameworks by employing transfer learning, because these specific frameworks take too much time to be trained, because we need a lot of time steps for these networks to work effectively. And also, it would be a very good idea to combine spiking neural networks with CNNs and RNNs, and also with different kinds of spiking neurons rather than the leak, integrate, and fire. These could be a very good perspective on the future voice for evaluating the performance of our network. Thank you all for your attention.